Hello students, in the previous class we have discussed the concept of DC machines as DC motor, and also we have derived the equation for back EMF, torque and also the speed of different types of DC motors, that is separately excited DC motor and self excited DC motor. In self excited DC motor we have studied that series motor, shunt motor and compound motor. Now today we will see how exactly we are going to solve the problems by using this back EMF and torque equations. In the first problem, it is given that it is a 4-pole 250 volt series motor has a wave wound connected armature with 1254 conductors. The flux per pole given is 22 milliweber when the motor is taking 50 ampere. Armature resistance is 0.2 ohm and series resistance is 0.2 ohm. So, we have to calculate the speed of the armature. Okay, first you collect the data given, and also it is given as series motor, and we know that in case of series motor the armature is connected in series with the series coil. Here this is A, then this is Z, or you can use that Y. Shunt will use this Z, series will use this Y. So, now we are going to give the DC supply, it is of the voltage V, or you can say it is Vt. So, current is going to supply in this sense. The series coil is connected in series with the armature. Current Ia is equal to Isc, that is equal to supply current I. So, now you collect the data given. So, that is the number of poles present in the motor is 4 and V is equal to this is equal to 250 volt, and it has a wave connected. So, that is wave connected means the number of parallel paths is equal to 2. Then the armature conductors we have 1254, and then the flux per pole is given 22 milliweber. Since it is given in terms of milliweber, convert this into Weber. So, it is 22 into 10 to the power minus 3 Weber, and motor is taking a current of 50 ampere. Armature resistance Ra is given, that is equal to 0.2 ohm armature resistance, and then the series field resistance Rse is also given as 0.2 ohm. Now, we have to calculate the speed of the armature. This is the problem definition. Now, you see that how exactly we are solving this problem to get that speed. We have the equation, that is Eb, where exactly we have considered this is the back EMF. Eb means the induced EMF opposes the applied voltage in this case, that is why it is called it as the induced EMF of the motor, we are going to call it as the back EMF. So, the back EMF equation with respect to the terminal voltage, we are considering it is V minus Ia Ra. Since the series coil is connected in series with the armature, the total resistance will be Ra plus Rse. Now, by using this relationship Eb is equal to V minus Ia Ra plus Rse, we can calculate this back EMF, that is equal to 230 volt. And we have the equation, that is generated EMF, that is Eb, the back EMF is equal to Zn 5p divided by 60A. Substitute all the data given in the problem, that is we have calculated this Eb, that is we have got it is 230 volt, substitute that Z is 1254, the number of conductors, N is unknown, phi it is given in the problem is 22 milliweber, number of poles is equal to 4, 60 divided by number of parallel paths, since it is wave wound it is A is equal to 2. Substitute the values and calculate the value of this speed of armature. We have got that N is equal to 250.1 revolutions per minute. So, this is how we have to solve the problem. So, first we have to collect the data and then we have to substitute in the equation to get the required answer. So, now you see that second problem. In this they have mentioned it is shunt motor. In case of shunt motor, the shunt coil is connected in parallel with the armature like this. Actually, in this slides, I have represented this small value of the resistance, that is the internal resistance of the armature, we have represented as RA, or otherwise within this itself we can represent RA. So, IA is flowing in this direction. So, because here you are going to give the DC supply and then this is the current drawn by the motor. Now, this current at this point, according to Kirchhoff's current law, it is divided into two parts. One is ISH, that is current flowing through the shunt field coil, and current flowing through the armature. So, now the total current I is equal to IA plus ISH. Therefore, armature current IA is equal to I minus ISH in the shunt field or shunt wound motor. So, here we can represent by using a resistor, or equivalently we can represent by using the symbol of coil like this. Okay. So, now what are the data given in this? Here the voltage given is 250 volt, it is shunt motor, takes a current of 20 ampere, resistance of the shunt field RSH is 200 ohm and of the armature is 0.3 ohm. Now, we have to find out the current in the armature and also the back EMF. So, what are the equations you are using and what is the data given? You see that line current is given, that is equal to 20 amps, means the current supplied by the source V, and then V is equal to 250 volts, RSH is 200 ohm, RA is equal to 0.3 ohm. We have the equation here, IA, armature current IA is equal to I minus ISH. Now, we have to find out this ISH. We know the value of I. When we are substituting the value of I and then after substituting the value, that is calculated ISH, we will get this IA. So, that is why we have to first find out what is the current flowing through the shunt field coil. So, ISH is equal to V divided by RSH. So, why we are using this equation? See here, this V is directly connected to these two terminals. So, now this will be the positive and negative, and since this voltage source is exactly parallel to this shunt field coil, the voltage across this shunt field coil is V divided by the shunt field resistance will give you the current ISH. So, now ISH is equal to V divided by RSH, that is equal to 250 divided by 200, we are getting this 1.25 ampere. So, after getting this ISH, substitute in this equation of armature current to get the value of armature current. We have got this is 18.75 ampere. So, here the line current given is 20 minus the ISH is 1.25, the total armature current what we are getting is 8.75 ampere. So, you see this problem, what are the aims of getting the values? That is, first one is the current in armature and the second one is back EMF. So, we have the equation of back EMF, that is EB is equal to V minus IARA. We have calculated the value of IA, we know the value of V, we know the value of IA, substitute and find out the value of EB. So, we are getting it is 244.375 volts. Now, we will see that third problem. In this there is slight difference. So, here the contact drop of brush is also given, it is per brush it is 1 volt. Now, you see this, it is a shunt generator. First in this problem we are considering both the shunt generator and shunt motor. Now, you see that how exactly when the this machine DC machine is working as shunt generator, what are the values, and when the DC machine is working as shunt motor, what are the values you are getting. A shunt generator delivers 100 kilowatt at 250 watt, the power is given, it is delivering 100 kilowatt at 250 volt when running at 400 rpm, the speed of the generator is 400 rpm. The armature resistance is given as 0.01 ohm and the field resistance is 100 ohm. If the same machine is run as a shunt motor, with an input of 100 kilowatt, because the generator converts the mechanical energy into electrical energy, motor converts electrical energy into mechanical energy. The output of this generator you are using as an input to this motor at 250 volt. Calculate the speed of the machine as a motor. As a generator, it is running at 400 rpm. Now, as a motor, we have to calculate what is the speed of the machine. Then contact brush drop is given, that is 1 volt per brush. Now, you see the connecting diagram for generator and motor. These two are DC machines, that is rotating machines, and also these are electromagnetic machines. Now, you see that how exactly we have considered the DC machine as a generator and also as a motor. In case of generator, the EMF will be generated here, and then you see that the current IA, according to KCL at this junction, IA is equal to IL plus ISH, because at this junction when you are applying the KCL, sum of the currents entering the node is equal to sum of the currents leaving the node. The sum of the current entering the node is IA, and then sum of the current leaving the load is IL plus ISH. This here the electric energy is generated and it is supplied to the load. In case of motor, you are giving electrical energy or electrical power as an input. So, and then you are going to convert that electrical energy into mechanical energy. Here you see that the current supplied by this DC source is IL, that is the line current, and then this has to overcome this shunt field and also this resistance. So, now IL is equal to IA plus ISH. So, this is the difference between the generator and motor. First, we will calculate the values when the motor is working as DC machine is working as generator. So, now the load current is given, that is I is equal to, so it is we have to calculate, because here power is given, voltage is given. So, the terminal voltage is 250 volt here, then power supplied is 100 kilowatt, 100 kilowatt divided by the voltage will give you the load current I. I is equal to 100 kilowatt divided by 250, that is equal to 400 ampere. Then shunt current, we have that shunt resistance RSH is given as 100 ohm. So, now V is given, V divided by 100 ohm will give you the current ISH, it is 2.5 amps. In case of generator, you see that I already told you this, IA is equal to ISH plus IL. Add IL and ISH to give the current IA, that is the armature current. You are getting this is 402.5 amps. So, what will be the drop? The armature resistance drop, it is IARA. Substitute the values and calculate. In this, we are getting 4 volts. And also here in this problem, they have mentioned that brush drop. Since the brush drop per brush is 1 volt, since we have the 2 brushes, we have to multiply by 2. So, now the total brush drop is 2 volt. The induced EMF in armature EG is equal to V plus IARA plus drop in brushes. Substitute these values and the whatever the value what we are getting is 256 volts. So, it is apparent that if this machine is to run as a motor at 400 rpm, so now the back EMF will be same, because the equations for EG and EB both are same. So, EB1 is equal to 256 volts. Now, in the first case, when it is running as a generator, in the first case the speed is 400 rpm. Now, you have to find out what will be the speed when the DC machine is running as motor. In this case, you calculate that input current, you will get the same thing, it is 400 ampere. The shunt current ISH is V divided by RSH, we are getting 2.5 amps, but in this case IA is the difference between I and ISH. So, in the previous you had this IA is equal to I plus ISH when it is working as generator, when it is working as motor IA is equal to I minus ISH. So, we are getting this is 397.5 amps. Now, we have the 2 drops, that is one is armature resistance drop, another one is brush drop. So, now for this particular value of current calculate IARA. So, we are getting that is 3.97 volt, the brush drop is 2 volt. And in case of this motor, we have that back EMF is equal to V minus IRA minus drop in pressures. Substituting these values, so we are getting that back EMF is equal to 244 volt. In the last class, I have derived the equation, that is the relationship between the back EMF and speed, and also the relationship between, so here in one more term you are considering, that is the flux per pole. In shunt motor, the flux per pole, in both the cases it will be same, because we are keeping that field current constant. When the field current is constant, the flux is also constant. That is why this phi 1 is equal to phi 2 in this case. Now, the relationship between the speed and back EMF will be N2 divided by N1 is equal to EB2 divided by EB1. Here, you know the value of EB2, you know the value of EB1, means when it is working as generator, we have considered it is EB1. When the machine is working as motor, we have considered it is EB2. The N1 is the speed when it is working as a generator. Now, you have to find out what is the speed when the DC machine is working as motor. So, substituting all the values, we are getting the speed of motor is equal to 381.25 RPM. So, this is how we have to consider the DC machine working as generator and motor. Generator converts electrical energy into mechanical energy, motor converts mechanical energy into electrical energy. So, now we will look into this problem, that is, in this problem the voltage given is 120 volt, it is also a DC shunt motor as an armature resistance of 0.2 ohm and field resistance of 60 ohm. It runs at 1800 RPM, means the speed of the motor is 1800 RPM. When it takes a full load current of 40 ampere. Find the speed of the motor when it is operating with half full load. Here, load you are going to consider that particularly in terms of this current. Okay, I given at full load is 40 ampere. Under off load condition, the motor is taking that half of that full load. So, that is why at off load we are considering IH is equal to 40 divided by 2, it is 20 ampere. Here also you are considering the two conditions, one is full load condition, another one is off load condition. First you have to calculate the required values at full load condition, then you have to calculate at off load condition, then you have to relate the values of full load and off load. So, now first you perform with that full load. These are the data given, V is equal to 120 volt, RA is equal to 0.2 ohm, RSH is equal to 60 ohm. Now, you calculate that shunt field current, ISH is equal to V divided by RSH, we are getting this 2 ampere. Now, full load current is given, I is equal to 40 ampere. Now, you have calculated that ISH, that is a shunt field current. Substitute in this equation to get the armature current, that is IA is equal to I minus ISH. Now, 40 minus 2 will give you this 38 ampere. Now, we have the equation for back EMF in terms of the supply voltage, EB is equal to V minus IA RA. Substitute the values. So, the EB in the first case under full load condition we are getting 112.4 volts. Now, we will see what exactly we are getting that EB in case of off load condition. So, current on the off load, as I already told, IH is equal to 40 divided by 2 means the full load current divided by 2, that is equal to 20 ampere. So, under this condition you calculate that armature current, that is armature current at off load is equal to armature current, this off load current minus ISH. ISH will be same in both the cases because voltage across the field coil is same and also the resistance is same. So, IH minus ISH, this is equal to 20 minus 2, we are getting that 18 ampere. Now, for this new value of armature current, you calculate what is this back EMF. Back EMF EBH at off load is equal to V minus IIH RA. In this case, we are getting it is 116.4 volts. Now, we have the equation, that is in the previous this problem also we have seen that N2 divided by N1 is equal to EB2 divided by EB1. So, by using this N divided by NH is equal to EB divided by EBH, we are getting the speed on off load is equal to 1864 RPM. Previously how much we had? So, the speed was, see here it is 1800 at full load. So, it is 1864 at off load. As the load decreases, the speed increases. So, now we will solve this problem. In this problem, the number of poles given are 4. Then the voltage V is equal to 500 volt. It is a shunt motor. It has 720 wave connected conductors. You see that it is wave connected. So, the number of parallel paths A is equal to 2. In its armature, the full load armature current is 60 ampere. At full load, the armature current given is 60 ampere and the flux per pole is 0.03 Weber. The armature resistance is 0.2 ohm and the contact drop, the brush contact drop is 1 volt per brush. Now, we have to calculate the full load speed of the motor. So, collect the data given in this. This is a shunt motor. The number of poles given is 4. The number of conductors Z is equal to 720. The flux per pole is 0.03 Weber. Then the number of parallel paths, since it is represented as wave connected, the number of parallel paths is equal to 2. The armature resistance is given as 0.2 ohm. Then the current, see the armature current at full load is 60 ampere, IA is equal to 60 ampere, V is equal to 500 volt. So, now what you have to calculate? You have to calculate the full load speed of the motor. Now, first find out this here EB is equal to, we have the EB and in this side you see that in the RHS there is a speed, okay. In the left hand side we have EB. So, in this case here EB is also unknown and also this speed is also unknown. Z is given, phi is given, P is given, A is given. So, now substitute the value of Z, phi, P and A, you will get EB is equal to 0.72 times speed, that is N is revolutions per minute. Now, you will have another equation to get that EB. EB is equal to V minus IARA plus brush drop. Okay. So, this is the relationship between back EMF and the terminal voltage. When you are substituting EB, the value you are getting, that is 486 volts. Here also EB you are getting this 0.72 N, but it is in relationship with the speed. Now, equate these two values 0.72 N and 486. When you are equating these two values, you are getting N is equal to 675 RPM. So, by using these two equations, both are the equations of back EMF. By using the equations of back EMF, you can calculate the speed when two parameters are unknown. Okay. So, we have got N is equal to 675 revolutions per minute. I will see the next problem. In this, you have to find out phi, that is the useful flux per pole. The voltage is given, that is 250 volt. It is 6 pole shunt motor having two circuit connected armature winding with 220 conductors. Z given is 220. At normal working temperature, the overall armature resistance including brushes is 0.2 ohm. Since this resistance is sensitive to temperature, it is expressed in relation with this temperature. At normal working temperature, the overall armature resistance including brushes is 0.2 ohm. So, the armature current given is 13.3 ampere at no load speed of 908 RPM. So, now collect the data given. In this, P is equal to 6, Z is equal to 220, A is equal to 2, RA, the armature resistance is equal to 0.2 ohm, IA given is, the armature current given is 13.3 ampere, the voltage V is equal to 250 volt. The no load speed is 908 RPM. So, we know the equation, that is EB in terms of this voltage, that is supply voltage, EB is equal to V minus IARA. So, when you are substituting the given values, we will get this EB is equal to 247.34 volt. And also we have one more equation, that is EB in terms of number of conductors, speed of armature, flux per pole and then number of poles and then number of parallel paths. Since it is wave connected, the number of parallel paths is equal to 2. Here Since we have already calculated this EB, substitute that value EB in this, it is 247.34. Here in the right hand side only phi is unknown. You substitute the other parameter values, you are going to get the useful flux per pole phi is equal to 0.0247 Weber. We will see the next problem. A DC shunt motor runs at 750 RPM from 250 volt supply. Here the supply voltage given is 250 volt and it takes a full load line current of 60 ampere. This line current given is 60 ampere and it is rotating at 750 RPM. Its armature resistance RA is 0.4 ohm and the field resistance RSH is 125 ohm. Assuming the brush drop, that is 2 volt, and neglect armature reaction effect, find the no load speed for a no load current of 6 amperes. Here full load current is given and also no load current is given. So, the full load speed is given, you have to find out the no load speed. Here also you have to use the equation, that is the relationship between the back EMF and speed. Collect all the data given in the problem. So, here at full load the motor is rotating at 750 RPM, the armature resistance is given, then shunt field resistance is given. At no load the current drawn is 6 ampere, at full load the current drawn is 60 ampere. So, we have to find out this no load speed. So, here we are neglecting that armature reaction drop. So, that is why we will consider that in both the cases the fluxes are same. At full load and also at no load, both the fluxes will be same. So, since the fluxes are same, so current ISH will be same. ISH is equal to V divided by RSH, that is equal to 250 divided by 125. This we are getting, it is 2 ampere. Then you calculate that armature current under full load conditions. The current drawn from the supply is given as 60 and then you have calculated this ISH, that is equal to 2 ampere. I is equal to I minus ISH. When you are substituting the values in this, we are getting this 58 ampere. Now, you have to use that value in calculation of this resistance drop. So, that is IARA. We have that the armature current is 58 ampere multiplied with the armature resistance 0.4 ohm, we are getting 23.2 volt. And we have the equation for back EMF, EB is equal to V minus IARA plus brush drop. When you are substituting this, we are getting EB is equal to 224.8 volt at full load condition. Now, you have to see that what is the value of EB, the back EMF under no load condition. For that, you have to calculate this. For full load condition, the current armature current is different, and then for no load condition the armature current will be different. This is equal to symbol, okay. Here by mistake it is minus is there. So, now you change that because I is equal to I minus ISH. Under no load condition we have used this subscript, that is with the symbol A naught, that is equal to I naught, the current drawn from this supply under no load condition, that is I naught, minus this ISH. ISH is constant in this. Now, you have to calculate IA naught. IA naught is equal to I naught minus ISH. So, since you have already calculated that ISH, substitute in this. The current drawn by the motor under no load condition is 6, ISH is 2, 6 minus 2 will give you the 4 ampere. Now, you calculate that armature resistance drop IA naught into RA, that is equal to 4 into 0.4, we are getting 1.6 volts. Substitute this drop in this, brush drop is given, that is 2 volts. So, EB naught is equal to V minus IA naught RA minus brush drop. So, this is equal to 250 minus 1.6 plus 2. So, this is equal to 246.4 volts. So, we have the equation, that is N divided by N naught is equal to EB divided by EB naught, means N2 divided by N1 is equal to E2 divided by E1. Substitute all the required values in this, that is motor running at full load speed, that is N, then this is back EMF under full load condition, back EMF under no load condition. Now, we will get you this the speed of motor under no load condition. Calculate like this. Now, this is also a DC shunt motor. Here you see that the no load current is given. So, it is, and the voltage applied is 230 volt, and it runs at 1100 RPM under no load condition. If the full load current is 40 ampere, find the speed at full load. Assume the flux remains constant and armature resistance is 0.25 ohm. You observe in this, in the previous problem, you calculated the no load speed, because here they have mentioned this full load speed. So, you had to find out the no load speed. In this problem, they have mentioned no load speed. Now, you have to find out that full load speed. And also it is given in this problem, assume the flux remains constant. Flux remains constant means ISH is also constant. You can find out this ISH by using voltage V divided by RSH, because the terminal voltage across this ISH is V. So, V divided by RSH will give you this ISH. In this case, you calculate the value, that is EB at no load, EB at full load, then use the equation of the speed and the back EMF relationship to get that the speed at full load. In this case, the given values are V is equal to 230 volt, the speed at no load is 1100 RPM, the resistance of the armature is 0.25 ohm, then the no load current of the armature is 2 ampere, the full load current is 40 ampere, and the fluxes, both the fluxes are same, because it is mentioned in this problem, that is flux remains constant in both the cases. So, we know the equations, EB is equal to V minus IARA. In this problem, brush contact drop is not mentioned. So, not necessary to take, since it is negligibly small, we are neglecting in this. EB is equal to V minus IARA. So, substitute the value of IA, substitute the value of RA, then we have this 230 volt, that is a supply voltage. So, this 220 volt is the answer for the first case. In the second case, you have to substitute, that is for the no load values. Okay. In this case, only this armature current is different. Armature resistance is in the both the cases, it is 0.25 ohms. Substitute the value of no load current in this, calculate EB naught, that what we are getting is 229.5. Now, you use the relationship, that is speed and back EMF, substitute the known values, that is N naught, EB, EB naught, get what is the value of speed at full load, that N is equal to 1054.5 ampere. So, now you see that you observe these two, at no load the speed is more, at full load the speed is less. Means as the speed increases, what will happen? As the load increases, the speed decreases. So, because the speed is inversely proportional to the load current. Now, we have done so many problems on the back EMF. Okay. So, here I took the example only on series motor and shunt motor. So, because you should know what type of problems in each particular type of motor you are going to get. So, that is why I am doing more problems on shunt motor. All varieties of problems I am solving on shunt motor. Okay. First you learn this, then we will see that what will happen in case only the relationship, the voltage equation, that EB and the terminal voltage relationship will change, and also in case of generator and motor we have seen that how exactly the current equation you are getting. This is IA is equal to I plus ISH in case of generator, and IA is equal to I minus ISH in motor. So, the EB equation will be same in all types of motors and also in generators. Only thing is the relationship between V and EB is changed. So, that is EG is equal to V plus IARA plus brush drop, that is in case of generator. in case of motor, the back EMF EB is equal to V minus IARA minus brush drop. Okay, and also we have used the relationship, that is N2 divided by N1 is equal to EB2 divided by EB1 multiplied with Phi1 divided by Phi2. In case of shunt motor, usually the flux Phi1 is equal to Phi2, that is why we have this equation N2 is equal to N1, that is equal to EB2 by EB1. So, I have solved most of the problems on shunt motor about this back EMF. Okay. Now, we will see that how exactly we are going to solve the problem for torque equation. In this case, we have to derive the total torque. So, in the last class, I have derived the equation for the torque. We have the two types of torque, that is one is armature torque, another one is shaft torque. So, armature torque, what it is developed, we are not exactly getting the same value at shaft, it is lesser than the armature torque. In this problem, they ask the total torque developed in a 250 volt 4 pole DC shunt motor with lap winding accommodated in 60 slots, each containing 20 conductors. The armature current is 50 ampere and the flux per pole is 23 milliweber. Here something is different in this to calculate the number of conductors. Slots are also mentioned, then the number of conductors in each slot is mentioned. First you collect the data given properly. So, here it is V is equal to 250 volt, then it is shunt motor with lap connected. In lap connected, the number of parallel paths is equal to number of poles. So, it is since it is a 4 pole machine, the number of parallel paths is equal to number of poles is equal to 4, and it is accommodated in 60 slots. The number of slots, what you are getting, number of slots mentioned in the problem is 60. In each slot you have slot per conductors. In each slot we have how many conductors? 20 conductors. So, total number of conductors is equal to number of slots multiplied with the conductors, number of conductors in each slot. How much we have? The total number of slots given is 60 multiplied with, we have 20 conductors in each slot. So, it is 1200 conductors. So, now Z is equal to 1200. Then armature current is given 60 ampere and the flux per pole is given, it is 23 milliweber. Since it is mentioned in terms of milli, so phi is equal to 23 milliweber, convert it into Weber, it is 23 into 10 to the power minus 3 Weber. Substitute these values in the equation. So, here our main aim is to calculate the total torque developed. So, now we have this equation to get the torque, Ti is equal to 0.159 phi Z Ia multiplied with P by A, it is expressed in terms of Newton meter. Okay. So, calculate this Z. So, Ia is given, phi is given, here you see that phi you can substitute, it is 23 milliweber, Z you have calculated 1200, Ia is given 50 ampere, number of poles is equal to P and also the number of parallel paths is equal to 4. So, A is equal to P is equal to 4, substitute. So, we are getting the total torque developed is 219.5 Newton meter. This is how we can calculate the target value. Now, you see in this problem it is a 250 volt. This is also DC shunt motor, takes 6 amperes line current on no load. The no load current is given, it is 6 amperes, runs at 1000 rpm. At no load, the motor is running at 1000 rpm. The field resistance is 250 ohm. This is RSH is 250 ohm and RA is 0.2 ohm. If the full load line current is 26, at no load it is 6 amperes. Now, the mentioned at full load is 26 amperes. Calculate the full load speed assuming constant air gap flux. Here flux is constant. See here, phi naught is equal to phi 1. Collect the data given, V is equal to 250 volt, N naught is equal to 1000 rpm, RSH given is 250 ohm, RA is 0.2 ohm, I1 is equal to 26 ampere, means full load current is 26 ampere. Now, to get this armature current, you have to calculate this ISH, because IA naught is equal to I naught minus ISH. The armature current is equal to line current minus shunt field current, current flowing through the shunt field. So, calculate this ISH first. It is voltage across the shunt field winding divided by the resistance of the shunt field winding. It is V divided by RSH. This is 250 divided by 250, because the given voltage is 250 and also RSH given is 250 ohm. So, it is 250 volt divided by 250 ohm, you are getting this 1 ampere. The armature current at no load is IA naught is equal to I naught minus ISH. This is 6 minus 1, this is equal to 5 ampere. Now, so in the second case, you have to calculate what is the armature current you are getting. Under full load condition, IA1 is equal to full load current, that is 26 drawn by the source, that is line current is equal to 26. ISH is same in both the cases because air gap flux is same. So, it is 26 minus 1, this is equal to 25 ampere. Now, in the first case it is IA naught is equal to 5 ampere under no load condition, under full load condition this armature current is equal to 25 ampere. Now, you calculate what is the back EMF under no load condition and under full load condition. Under no load condition, you have this back EMF equation is equal to V minus IA naught. This is the armature current under no load condition multiplied with the armature resistance. EB naught is equal to V minus IA naught RA. After substituting the required values, we are getting it is 249 volts. Similarly, you calculate this back EMF under full load condition. This EB1 is equal to V minus IA1 RA. IA1 is the armature current at full load condition multiplied with the armature resistance, and subtract this value from the supply voltage, that is equal to 250 volt, we are getting it is 245 volt. So, no load speed is mentioned, only unknown is you have to find out the speed at full load. So, we have the equation, that is N2 divided by N1. In generally, when we are expressing N2 divided by N1 is equal to EB2 divided by EB1. Substitute the values, this is speed at full load condition divided by speed at no load condition is equal to back EMF at full load divided by back EMF at no load. After substituting the calculated values, you are getting the speed at full load N is equal to 984 rpm. So, this is how this problem is to be solved. Now, in the next case, you see this. Here in this problem, they have mentioned it is a 4-pole DC machine, P is equal to 4, it is also DC shunt motor. DC shunt motor takes 22.5 ampere, then V is mentioned, that supply voltage 250 volt, RSH given is 125 ohm, and then RA is equal to 0.5 ohm, it is mentioned in the problem. Now, the armature is wave connected. Wave connected means the number of parallel paths is equal to 2 with the conductors, the total number of conductors given is 300. If the flux per pole phi is equal to 0.02 Weber, we have to calculate first speed and then we have to calculate the torque developed TA, and then we have to calculate P. So, here in this equation the speed. So, what is the equation you are using? EB is equal to Zn 5P divided by 60A. Here Z is mentioned in this, the total number of conductors. So, speed is not given, then flux is given, P is given, A is given. In this, EB is not given. EB and N both are unknown. Now, how to calculate this EB? We have one more relationship in this. EB is equal to V minus IA RA. So, here the load current, the line current is given. So, current supplied by the source V is given. So, that is equal to 22.5 amps. Then we know that IA is equal to I minus ISH. ISH you have to calculate. ISH is equal to V divided by RSH. Calculate and substitute in this I you know, then you can find out this EB. Substitute that EB in this equation, you are going to get this speed. So, this is how you have to calculate, and then you have the torque equation, you have the power developed equation, you can calculate all the three requirements of this. So, that is speed is equal to N is equal to EB into 60A divided by Z5P. So, we are getting that speed is equal to 1199 RPM, and we have the equation for torque. TA is equal to 0.1595 Z IA multiplied with number of poles divided by number of parallel paths. Substitute all the values given in this, we are getting the armature torque developed is equal to 39.1 Newton meter. We know that the power developed equation is equal to EB into IA. Substitute EB calculated in this, that is 239.75 multiplied with the current I is equal to I minus ISH, I is given, the current drawn by the motor minus this ISH is calculated, that is 2 ampere. Now, IA is equal to 20.5, substitute in this. So, you will get this power developed EBIA is equal to 4.915 kilowatt. It is expressed in terms of kilowatt. Now, we will see this problem. This is also a shunt motor as an armature resistance of 0.6 ohm and the voltage V is 230 volt. If the full load armature current is 30 ampere, no load armature current is 4 ampere, find the change in back EMF. Here, since the armature current is changed, the back EMF will also change from no load to full load, because we have the relationship EB is equal to V minus IARA. In both the cases, the current will change. No, here you see that this IA armature current at no load is given as 4 ampere. Armature current at full load is given as 30 ampere. Since the armature current is changed, the back EMF will also change. So, use this equation EB is equal to V minus IRA to calculate the back EMF under both the conditions. So, under no load condition EB naught is equal to V minus IA naught RA, we are getting 227.6 volts. Under full load EB1 is equal to V minus IA1 RA, we are getting 212 volts. There is a change in back EMF from no load to full load. What is the value you are getting from no load to full load? It is 15.6 volts. So, I think I have covered most of the problems with that back EMF and torque. That is only one motor I have taken as an example, that is shunt motor. Only one problem I solved on series motor. So, most of the concept we can understand with the shunt motor, that is why I took shunt motor as an example. So, I have solved most of the problems on this shunt motor. In the next class, we will see the characteristic of DC motor, applications of DC motors. So, how exactly the speed torque characteristics and then current characteristics you are going to get for different types of DC motor, that is series motor, shunt motor and compound motor. Thank you very much.